Welcome to this webinar on applying the ABB ACH580 ULH drive to power factor correction. My name is Thomas Shircel. I'm a Senior Regional Application Engineer for ABB, and I'll be the presenter for this webinar. Let's take a look at the agenda for this presentation. We're going to take a look at an overview of power factor, how an ultra-low harmonic drive operates, ULH power factor correction ability, available parameters, active power factor correction, continuous power factor correction, and additional effects of power factor correction. And then we'll have a summary. So let's take an overview of power factor. We're about to start an overview of power factor, but online we have Introduction to Power Factor available on YouTube. It's a more extensive overview of power factor and how power factor applies to your facility. So why does power factor matter to you? If you're a building owner, power factor correction can lead to cost savings by reducing demand charges from utilities. And that's a big point of this whole entire webinar, is if you can reduce your demand charges from utilities, you can save money. As energy efficiency becomes more increasingly important, optimizing power factor can lead to a significant cost savings and reduce environmental impact. A poor power factor can cause issues with your building stability and reliability. With the increase in integration in renewable energy sources and smart grid technologies, maintaining a good power factor is crucial nowadays. Future system designs, new devices, equipments, and systems are developed that can affect power factor. Updating and monitoring techniques allow for utilities to price based on power factor. Standards and codes related to power factor will lead to more restrictions in the future. Let's take a look at what bad power factor does to you. Impacts your facility's efficiency. It's increasing stress resulting in lower operational life of your equipment. Lower electrical load capacity is created. Potential regulatory compliance issues can happen. Many utilities charge an extra fee for low power factor. It has an environmental impact because more fuel is burned at the power plants, causing higher greenhouse gas emissions. Good power factor. Better efficiency, increased load capacity, reduces losses at a higher power factor means less wasted energy and a lower energy consumption. It lowers utility billing. Many utilities give you extra credit for a high power factor. Efficient use of electrical power reduces the burden on the electrical system as a whole. Equipment experiences less stress, fewer faults reducing downtime, and longer operational life. Voltage regulation, electrical components, and conductors experience less overheating when power factor is high. Now we need to look at the types of power factor we have. Displacement power factor. We'll look at the power factor triangle. We're going to do a little bit of math here, nothing super complicated. We have a vector here. It's going to be your active power in watts. Next thing we're going to look at is reactive power, and that's volts, amps, reactive. And that's in green. Then we have our apparent power. That's the vector summarization of the volts, amps, reactive. That's your triangle. The displacement is the power factor. It's the cosine theta. Cosine theta shown here is your power factor. And kilo is for 1,000 times. And so 2 kilowatts equals 2,000 watts. Power factor base equations are real simple. Real power divided by apparent power equals watts over volts amps, and that's power factor. Apparent power equation is the volts amps of the square root of the squares of the watts and the volts amps reactive. And a power factor triangle is power factor equals cosine theta. So this is displacement power factor. One of the things that we have to understand is displacement power factor can be corrected by a ULH drive. Let's look at true power factor. We'll start with a true power factor box. Initially, we have our active power in kilowatts on our horizontal plane, and then we have our reactive power, kVA, and reactive on our vertical plane. Connecting together, it gets our apparent power in kVA. That was our displacement power factor, and that's your triangle. So we're going to take this triangle and move it around a little bit. I'm just going to move your reactive power over to the left. Then I'm going to add reactive power and distortion. That's your kVA distortion, kVAD. That's going to be going out into the back plane. At this point, we'll draw a box, connecting all the corners together. When we complete this box, we can look at apparent power now, which is your true power factor. That goes from the lower part of the box to the upper part of the other side of the box. And it is actually a longer vector than we had before. So a true power factor base equation is power factor equals cosine theta, which was your displacement power factor, divided by the square root of 1 plus the total harmonic distortion and current squared. Let's talk about the effects of displacement power factor and how you can save money. This is an example of a 75 kilowatt system, and we're looking at improving the power factor from a 0.6, 60%, to a 0.9, 90%. Looking at 75 kilowatts and looking at a 0.6 power factor, we can build up our displacement power factor triangle. We have 75 kilowatts in red. We have a 0.6 power factor. This is going to give us 100 kVAR, creating our new displacement power factor at 125 kVA. If we do a correction on this from a 0.6 to a 0.9, we create a new triangle. And we'll look at our kVAR again. That's now went from 100 kVAR down to 36.3 kVAR. And when we look at our power factor kVA, we now have 83.3 kVA. So we went from 125 kVA to 83.3 kVA. We also reduced our load amps from 151 amps down to 100 amps. We also reduced our total kVA needed for a transformer from 175 kVA down to 100 kVA. And we've also reduced our required wiring from a 2-aught to 3 gauge per phase. Other savings include electrical billing, power factor penalties and fees, power distribution equipment costs, and component life expectancy. Let's look at the effects of power factor and cost multipliers for displacement power factor. Table 2 here comes from Indianapolis Power and Light Company, and it's for over 50 kilowatts of usage per month. We're going to start out with a power factor of 0.85. That's the multiplier of 1. If you have a 0.85 power factor, your multiplier is 1, therefore your kilowatt per hour is your kilowatt per hour. Now, if you get better than a 0.85 power factor, the power company gives you a discount. If you're worse than 0.85 power factor, the power company will penalize you for it. So let's look at our power factor of a 0.6. That means your multiplier is a 1.1785, which means it's approximately 18% more in cost per kilowatt. Change our power factor to a 0.9, our multiplier goes to a 0.981. That means you basically get a 2% less cost, a credit, in how much you pay for your power per kilowatt. So if you look at the difference between a power factor of a 0.6 and a power factor of 0.9, you can basically look at your over 19% in cost savings. Let's take a look at how ultra-low harmonic drive, the ULH, operates. We're about to do a short review on how an ultra-low harmonic drive works. We do have a video on YouTube demystifying ultra-low harmonic drive operation that goes through how the ACH580 ULH actually operates. We're going to talk about the basic power structure for a ULH drive. When looking at the power structure, we have an LCL filter built into the drive. We have what we call our line supply unit. This is a set of IGBTs on the input of the drive. This LCL filter and the line supply unit makes the active front end inverter/converter. We have a DC bus, and we have our inverter unit, our INU. The INU unit supports the motor. So what happens inside of a ULH drive? We'll take our 460 volts, 60 hertz coming into the drive, and we'll look at our active front end inverter/converter. The LCL filter and the line supply unit uses pulse width modulation to create 60 hertz. That pulse width modulation is considering phase angles to the input power. The DC bus gets charged depending on how we modulate the front of the drive, and we get a DC voltage. That DC voltage is sent to the INU, the inverter unit. The inverter unit supports the motor by creating a new frequency and a new voltage. So let's break down the front end of the drive. Look at some waveforms on the front end of the drive. Looking at the line supply unit, the voltage between phase A and B, we see our pulse width modulated voltage being created by the input of the drive. In the filter, we now see a voltage which looks like a sine wave. And on our input of the system, we have our line voltage coming in. This is going to be a quick overview of how the line to the active front end side of the drive works and how power factor can be adjusted. This is done through voltage. So looking at our first scenario, we're going to look at a lagging power factor of 0.956. Our voltage in the line is in blue. Our active front end voltage is in green. When we look at our vectors, what ends up happening is we need a new vector for IX. That's our current vector. Our current vector, because it's not in line with the voltage of the line, it's in line with the voltage of the active front end, is lagging. And if you look at the peak of the current, it's lagging behind the voltage of the line. So in this case here, we have a lagging power factor. If we turn around and change this a little bit by adding more voltage to the active front end, we can line up our differentials in voltage Vx, and what ends up happening is Ix is now in line with the voltage line. And that means is here our blue line is input power, our orange line is the current now, and they're both peaking out together, they're both in sync with each other, and the green is actually the active front end. This creates a power factor of unity by keeping the actual line voltage and the current in sync at the input. That is a unity power factor. You can look at this the other way. For a leading power factor, we can actually create the voltage of the active front end to be even higher. This causes the IX to be at an angle, which means it's no longer in line with voltage line. And if you look closely, what we see is a peak for our input voltage here, but our peak of our current is actually in front of the voltage. That is a leading power factor right there. So by pushing this vector out even more, we can change our current on the front end of the drive. And we can bring it back down to unity again by going to where we were before. And when the current lines up with the voltage, at this point, we're at unity again, which means the voltage is in sync with the current at the input of the drive. The drive has the ability to manipulate this and change it as needed. Let's take a look at an overview of a ULH drive and how it operates. The LCL filter is integrated with the ACH580 drive. The LCL filter reduces 9 notches that are produced during the operation of the line supply unit. The inductance of the filter also provides impedance between the line supply unit and the line. The line supply unit consists of 6 IGBTs, and together with the LCL filter, this creates the active front end, the inverter converter. The line supply unit uses IGBT technology, IGBT switching to supply energy to the drive or to regen energy from the drive. It controls the magnitude and direction of current flow and the power factor. It controls the voltage on the DC bus. The INU, the inverter unit, uses IGB technology. The INU creates a new voltage and frequency to control the motor by creating a pulse width modulated output. ULH power factor correction abilities. When looking at the ULH power factor correction ability, one thing to look at is drive loading. HVAC systems are designed for the worst case situations, the coldest days in winter and the hottest days and most humid days in summer, with the highest occupancy. For the most part though, all the other times the HVAC system is oversized. Because these effects, the ACH580 ULH drives have the available energy that can be used for power factor correction. So when we look at ULH power factor and correction abilities, the active front end can have unity power factor throughout most of its power range. The ACH580 ULH drive can adjust the input power factor for positive or negative through programming. This allows the drive to use its remaining capacity to further correct the building's power factor whenever it's not running at full load. The drive can be programmed to create kVAR to counter-react the power created by other components, thus improving the facility's displacement power factor. When looking at the ACH580 ULH, maximizing reactive power while delivering demand to active load is very important. At 100% reactive power, the reference is going to be in green right here. That's my reference. I'm going to ask for 100% reactive power and no active load. With no active load, no motor load, the ULH drive will be restricted to 80% of its total reactive current possible. This is done because we need to be able to start the motor. The current in the LSU is restricted to 80%. Even though the demand is asking for 100%, so we end up with IQ, the total reactive current. As we start to load down the drive, loading down with the motor, what happens is we'll leave our reference at 100%, and we have a load. Now, LSU's current will move up to its 100% ability, and it will support the load, and it will support a large amount of actual reactive current. We can continue on to 100% reactive power reference and a large active load. We end up still with probably a small amount of reactive current being put into the system. This is because the line supply units are sized for the drives by frame sizes, and the line supply units are capable of a bit more energy than the actual loading of the actual drive's size for the motor loads. But when you look at motor loads, a lot of times the motor loads don't equal the total output of the drive to start with. Basically what's happening is the line supply unit, you'll very probably have extra energy even under full load scenarios to support power factor correction. One of the application options we're going to look at is active power factor correction. We're going to use the facility's power factor meter and the building management system or the energy management system to continuously apply power factor correction to your system. The BMS EMS uses power factor meter data to update all the ULH drives and monitors the feedback to continuously collect the total power factor correction. The advantages of this is it allows for the optimal correction for maximum effect. It reduces electric billing and it varies all drives to contribute to the correction of the system. A disadvantage is the total correction is limited by each drive's loading, the power factor metering is needed, and the BMS or EMS requires to control a drive settings. Another option we're going to look at is continuous power factor correction. Continuous correction option, if the building has a load that's consistently with continuous lagging or leading power factor, the drives can be set to a leading or lagging power factor to displace the power factor of the building. We can use data over time collected from metering or electric billing for this information. Single or multiple ACH ULH drives can be programmed to correct the power factor. The total kVAR programmed to correct the kVAR is for the best power factor to be better power factor ratings. We'll go through this a little more extensively later in this presentation. The advantages is it's simple to apply, it reduces electric billing. The disadvantage is limited to correction abilities, and the total correction is limited to each drive's loadings, and there's a potential for overcorrection if not programmed correctly. Let's look at our available parameters that we have for doing the programming. We have a multiple set of parameters that are relatively giving you direct information about power factor and what the system can do. Some actual value parameters are like line current. The line current estimates the line current flowing through the supply unit in amps. This current is moving into the drive and is real current, and it's the drive loading on the grid. Then we have active current. Active current estimates the amount of current flowing through the supply system in amps. This current is used to support unity power factor. When the system is programmed for leading or lagging power factor, the active current is the current applied to support the motor loading, not what's actually happening to the whole system. Reactive current is estimated reactive current flowing through the system in amps. If the line supply unit is creating leading kVAR, the current reading will be positive. If the line supply unit is creating lagging kVAR, the current reading will be negative. The total active current and reactive current may not add up to the line current due to the application and the total ability of the line supply unit's rating. We have grid power apparent. So the apparent grid power estimates the parent power being transferred through the supply unit in kVA. Then direct grid power estimates the power being transferred through the supply unit in kilowatts. Grid reactive power estimates reactive power being transferred through the supply unit in kVAR reactive. We can look at LSU cosine theta. This is the power factor of the supply unit. The value of 1 is unity. Positive values between 0.01 and 0.99 represent leading power factors, and negative values between negative 0.01 and negative 0.99 represent lagging power factors. Now, this is from the drive's point of view. Let's just say that you had a 0.6 power factor, or 60%, and that's a positive number. That would mean that you had a lagging power factor on your facility system. And if you had a negative 0.6 power factor, that would mean you'd have a leading power factor. That is reverse of what the drive is doing. For the drive is saying when we have a 0.6 power factor that we are creating a leading power factor, not a lagging power factor. So we're creating a leading power factor because it's a positive number, and that's going to counteract the power factor in kVAR of energy in your facility. Reactive power reserve indicates how much reactive power capacity remains in kVAR. The kVAR indicates how much reactive power the LSU can apply to power factor correction. This will vary depending on loading of the drive. LSU nominal power is the maximum power the LSU can support in kilowatts. This represents the total power of the LSU for the drive. The actual amount that can be used for power factor correction is limited to 80% of the nominal power. Now let's look at group 94. 9401 is your LSU control. This allows you to enable or disable, on or /off, the internal INU and LSU state machine. So what is that? What it comes down to is the ACH580 ULH drive has an output section to control the motor and an input section, your line supply unit section. Normally, you don't have to worry about this part in this system. For control of this, you want it to the default of on. If you turn it off and you go in to try to do some programming, you won't be able to send information over to the line supply unit. The default is on, so we leave it on. When the drive is powering up, the status of this may change because certain things are happening, but it will go back to its original setting. The next thing we have to look at is 9402. That's the LSU panel and communication control. This enables the ability for things like drive tools to communicate to parameters in the line supply unit. It also allows you to go to the keypad and change parameters in the line supply unit. If you were to attempt to go into certain parameters in the line supply unit and try to change them, like 9411 LSU stop delay, if you wanted to change that and this parameter was disabled, on the keypad, you wouldn't be able to change those parameters. You want to have this enabled, and that allows you to go into the line supply unit and do changes either through communications or through the keypad. Line supply unit stop delay, parameter 9411. This defines the stop delay in seconds. Default is only 600 seconds, otherwise 10 minutes. After 10 minutes, if the drive is not loaded down, the drive will stop modulating its input and disconnect the input filter from your system. You can adjust this all the way up to 3600 seconds, which is 1 hour. And you want to set it to its maximum setting so you can keep on performing KVAR correction beyond the point when the drive stops. User reactive power reference. The reference is defined reactive power by the supply unit. It can be programmed from multiple settings through parameter 9433. Parameter 9433 determines what parameter 9432 is set to. So we look at 9433 right here, user reactive power reference type. This is adjusting 9432 above it as to what you're going to set it to. You can do different decimal points on KVAR, or you can set it to Q reference and percentage, or you can actually put the cosine theta into it. In this section, we're going to look at active power factor correction. Our whole objective here is how to actively update a system and correct power factor to save money. One of the things we're going to need in your building or your facility is going to be a meter that monitors displacement power factor and has the ability to communicate with your BMS. You want this meter as close as possible to the input power of your building because that's where the power going out to the power company is, and that's where your power factor correction is most important. You need a building management system that's tied into the power factor meter and tied into the ACH580 ULH drives. The building management system can be programmed to monitor the power factor meter and supply the ULH drives with power factor correction information. Then you need ABB's ACH580 ULH drives, and it needs to be tied into your BMS. The more drives in the system will allow for higher average abilities for correction of KVAR. So let's look at our full system control here. Multiple devices can affect the overall power factor of a building. A 6-pulse drive does create a little bit of power factor displacement. It's usually around 0.97, so that's a lot better than a motor across the line. Line start motors, a lot of times at full loading, can be around 0.81 to a 0.9 nowadays. When line start motors are not fully loaded, its power factors go much farther down. Office supply equipment like lightings, UPS systems, medical equipment, AC-DC converters, DC drives, and transformers all contribute to a power factor error. Almost all these devices create lagging power factors. The ACH580 ULH drive is used for power factor correction if you want to. Most of the year, the drives are not fully loaded, and the BMS can feed correction requirements directly to the drives. The BMS can update to do the feedback from the power factor meter. Programming the drive to accept power factor correction from your building management system is easy to do. 9401 and 9402, by default, 9401 is set to on and 9402 is set to enable. This allows the front of the drive to accept updates and the programming to be done through the control panel or drive composer. Now you can change other parameters on the front of the drive, and this is by default. The line supply unit stop delay, you want to set to maximum. This allows the ultra-low harmonic drive to continue to do active power factor correction for as long as possible. 9433, this parameter affects 9432. And 9432 is where you send your information from your building management system to do your power factor correction. By recommendation, if you send it to Q reference percentage, now all you have to do as your building management system is send a number as a percentage to 9432. And that's your update, your percentage of what you need to do for KVAR correction. Parameter 9432 will accept the value of percentage of correction to the building management system. The drive will contribute the overall correction of KVAR. A positive percentage will produce a leading power factor. Now, this is reverse of the other system, as I said earlier. A positive percentage will produce a leading power factor, otherwise a negative power factor, to correct for a lagging power factor. When you look at the drive's point of view, a positive percentage creates a negative power factor to correct for the lagging power factor of the system, which is a positive power factor. Now, a negative percentage produces a lagging power factor. If you have a leading power factor in your system, you send a negative percentage number to the drive to correct for the leading power factor of the system. It's reverse of what you're used to, but it's from the drive's point of view. When set up, as the facility's power factor approaches the desired power factor, percentage of correction needed will reduce. As individual drives change their load and the ability to do corrections in K-bar will change, causing the BMS to correct for the total percentage needed. Adjusting the BMS PID loop allows for stable correction, compensating for the time delays in correcting from the drives and the feedback from the power factor meter. As the building loading changes, the BMS will change the demand percentage on the ULH drives. Feedback set point should be close to the unity power factor, but to prevent a leading power factor, you may wish to set the set point to a 0.98 or a 0.99, and this will depend on the updating speed of your system as to what you feel safe doing. One of our built-in communication systems with the ACH580 ULH drive is BACnet MSTP, and the addressing is all set up already in the drive. So the analog values and the object IDs supporting allow multiple data points for power factor correction. One of the most important ones is AV119, and that is your user reference power reference that allows you to write the parameter 9432, changing the level of power factor correction as needed. For more information, refer to the ACH580 BACnet protocol documentation. Another native language built into the ACH580 drives is Modbus RTU, and we have a Modbus RTU addressing system in place. The Modbus registered numbers for 32-bit reads of the 580 series drive parameters requires some math to convert the parameter numbers into register numbers. If parameter 5833 addressing mode equals 0, the default setting, this allows for both 16-bit and 32 read-writes of parameters. The math of the equation for the 32-bit Modbus register is 420,000 plus 200 times the parameter group plus 2 times the parameter index. So for example, parameter 9432 user reactive power reference would be 420,000 plus 200 times 94 plus 2 times 32. That's 438,864. The addressing mode setting of parameter 5833 allows for the 580 series to register read as a 16-bit and another read as a 32-bit without having to adjust any other settings. Now let's take a look at another option. This is continuous power factor correction. For continuous power factor correction, we are going to look at buildings that have a continuous power factor issue. We need to note the building's power factor ranges. So for facilities with a documented power factor range, this can be done. Data over time is collected from metering or the electric billing information. A single or multiple ACH580 ULH drive or drives can be programmed to create a certain amount of K-bar to do power factor correction. No feedback to change the K-bar settings is built into the system. You'll program the drives for a certain amount of K-bar, and that's what the drives will do. The total K-bar program is to correct the K-bar of the best power factor to a better power factor rating. We'll go through this in a second. Let's take a look at an example now. We're going to have a facility with a 75 kilowatt load, and it's going to have an average displacement power factor of 0.80, resulting in a total K-bar of 56.3 lagging. After review over time, the displacement power factor can be as good as a 0.85 and as bad as a 0.75. So looking at the system, we're going to go back to our triangle right here, and we're going to convert power factor to degrees. So that's an arc cosine of 0.8, and that gives me 36.86 degrees. And if I start calculating out the hypotenuse of the triangle, which would be S, apparent power, I will take the active power, P, divide it by the cosine of the angle. That's 75 kilowatts cosine 36.86, which equals 93.75 kVA. I still need to get reactive power, Q. To get reactive power, Q, I turn around and take the square root of the apparent power squared minus the active power squared. So that's a square root of 93.75 kVA squared minus 75 kW squared, which equals 56.3 kVAR. And that's our kVAR that we're dealing with that we want to bring back onto the system to resolve the problem. Now, we have to look at the system though. With the highest power factor of 0.85 equaling 46.5 kVAR, the ACH580 ULH drive can be programmed to counter the 46.5 kVAR. Programming for more 46.5 kVAR could cause the system to be overcorrected, causing a leading power factor. So we have to look at the best scenario we have right here, and the best scenario is a displacement power factor of 0.85, and correct for that, aiming for a power factor close to 1 unity. All available ACH580 ULH drives should be reviewed for the average loading, so there's available active power and the amount of time the drive is running to get the best bang for your dollar. After reviewing our system, we'll see that we see 3 drives that have lower loadings that can be used for correction, and then we can turn around and disperse the actual kVAR amongst the 3 different drives. So we can program one drive for 18 kVAR, the other one for 20 kVAR, and one for 8.5 kVAR. This will give you your total correction around 46 kVAR, 46.5 kVAR, and that will allow you to have the system working. So programming for continuous correction is easy on the ULH drive. Really simple. 9401 needs to be set to on, that's default. 9402, your panel communications should be enabled, that's default too. That allows you to change parameters. 9411, the stop delay, we want to create that to the maximum point to do the most amount of active correction we can. 9433 is where you set your set points for 9432. So 9433, we need 1 decimal point, so we're looking at option 0, Q reference kVAR 1.0. 9432, user reactive power, now can be set for the parameters that we need. We can program each individual drive. The 3 drives we're going to program. One driver we're going to program for 18 kVAR, the other for 20 kVAR, and the last drive for 8.5 kVAR. That's going to build up our 46.5 kVAR of correction to our system. Additional effects of power factor correction. We have another additional effect that occurs when you're doing power factor correction, and this is the relationship of your total harmonic distortion to the amount of motor load power that you have in your system. So total harmonic distortion, when the drive is fully loaded, it normally is keeping its total harmonic distortion at 3% or less on most systems. When the ULH is performing power factor correction, the line supply unit is loading up through its power range. If I look at no power factor correction, the input of the total harmonic distortion increases as the motor load decreases. When the motor load starts getting below 40% of the power level, the actual amount of distortion starts to increase. When we get down to about 10%, it starts to increase quite a bit more. And I'm talking about motor power load, not the actual just amperage, the actual amount of power going to the motor. If I add just simple 10% of drive power factor correction, reduce the total harmonic distortion on low motor loads, as shown in the gray line, compared to the blue line. If the drive is providing 100% available correction, the total harmonic distortion and current can stay as low as 3% throughout the full motor load range. What's happening is the active front end of the drive is actually working on doing kVAR correction. Therefore, it's keeping its active front end fully loaded down and keeping the filter loaded down, doing kVAR correction on your system. And your total harmonic distortion and current is being kept below 3% or around 3% at very, very low loads. Another additional effect for power factor correction is standby generators. The power factor directly affects the efficiency and capacity of overall performance of standby generators. Generator's kVA rating is based on unity power factor, and when lagging power factor is present, higher losses in the generator windings cause lower efficiencies. Generators need to be increased in size to support the load increase in cost because the generator must supply both real and reactive power to your system. Leading power factor will make the generator unstable and trip offline. A slight bit amount of leading power factor is okay, but once you get into the unstable region, you will trip out that generator. The ACH580 ULH drive has unity power factor and low harmonics, allowing for the kW of the generator to equal to the kW of the loading size. Also, for other loads, if the drive is used to do kVAR correction, the generator loading is reduced. It's time to sum up what we've learned in this webinar. Power factor correction can lead to cost savings, reducing demand charges from utilities. An energy-efficient system becomes increasingly important. Optimizing power factor can lead to significant cost savings and reduce environmental impact. A poor power factor can cause issues with your building stability and reliability. The ACH580 ULH drive can have unity power factor through most of its power range, and the ACH580 ULH drive can adjust the input power factor to a positive or negative through programming. This allows for the drive to use its remaining capacity to further correct the building's power factor whenever the drive is not running at full load. The drive can be programmed to create K-bar to counter reactive power created by other components, thus improving the facility's displacement power factor. When the ACH580 ULH drive is providing power factor correction, the total harmonic distortion can stay as low as 3% throughout the full motor loading range. The building management system can be set up to do multiple ACH580 ULH drives and contribute to the overall displacement of power factor correction. This concludes this presentation on applying the ABB ACH580 ULH drive to power factor correction.